Let's start lecture 30. And we will continue our discussion on kinetics of corrosion. And we have been discussing on current density. And we saw the concept of I0 also, which is called exchange current density, which appears when for a particular redox reaction, for this particular redox reaction, when it reaches equilibrium. So, that means then this is a kind of situation which is reversible, as well as this is non-corroding. Why it is non-corroding? Because when a metal is dipped in an aqueous medium, the metal ion comes out from the metal surface, as well as the reverse reaction, which is the metal ion gets reduced to metal. These two processes happen at the same rate, and that is the condition when we have the exchange current density. The metal ion formation, which is M goes to Mn plus Ne, this is corrosion, or we can take it as anodic reaction or oxidation reaction. And then this backward reaction, which is reduction or cathodic reaction or deposition reaction. Both this process happen at a same rate, and the rate is termed in terms of I, which is the exchange current, which is basically the current density. Since we have seen that I A divided by N F is nothing but the rate of metal dissolve in gram per unit area and per unit time, where A is nothing but atomic weight of that particular metal, N is the number of electrons that participate for this reduction reaction or oxidation reaction, F is 1 Faraday. So, this particular term we call it as IC, and this one as IA. IA is nothing but the corrosion current density. And in order to indicate the direction of flow of these two currents, we have put a negative sign in front of IC. This negative sign does not indicate that the value of current density is negative, it indicates that it flows opposite to the anodic current or the corrosion current density. Now, when they reach equilibrium, we come across I0, which is the exchange current density, and that is basically the reversible condition and non-corroding situation, because whatever metal ion forms, that metal ion goes and deposit on the metal surface. Now, once we know this I0, we need to look at little bit carefully on this I0, because this I0 is a very, very strong and fundamental kinetic parameters. And this parameter would have a huge importance on the corrosion of a particular metal in a particular medium. And that we will see little later when we start discussing on mixed potential theory. Now, if we see this I0, we have said that this is specific to a particular redox reaction. It is not for the complete cell reaction, this is for a half cell reaction, I would say. For example, if we take this consideration like zinc plus HCl equal to zinc chloride plus H2, for this reaction it can be broken into two half cells. One is zinc minus 2E equal to zinc plus plus, and 2H plus 2E equal to H2. This is the gas that forms on the zinc surface. So, it is experimentally we have seen that when zinc is dipped in HCl, let us say that HCl is pure HCl and it does not contain any oxygen. So, that means it is a deaerated solution. That time we have these two half cell reactions. So, for each half cell reaction we will have corresponding I0, and in this case how do I denote this? It should be denoted like this. This is I0, this is also I0 for H plus H2. So, for the reduction reaction we are considering this is the notation we would use, and now question is this I0 indicates some equilibrium reaction of that particular metal ion disposition or dissolution, or hydrogen ion formation or hydrogen gas formation. Now, those reactions happen on a particular surface, and in order to indicate that this is taking place on a particular surface, we have to also indicate on which surface this is taking place. So, in the bracket we have to mention zinc, because on the zinc surface only that zinc dissolution takes place, as well as hydrogen evolution also takes place on the zinc surface. So, zinc. So, now exchange current density I 0 on a metal surface, and then so this is the notation, and now this particular redox reaction which is half cell reaction. See, for example, this is for a half cell, this is for a half cell, and their combination they are constituting one complete full cell reaction. Now, this particular reaction might change, it could be metal dissolution or it could be any other cathodic or anodic reactions that are taking place on this metal surface. For example, in this zinc case, zinc dissolution is taking place on from the zinc surface, and that is what we are considering I0 for zinc dissolution on zinc, as well as hydrogen evolution is also taking place on zinc surface. That is what we are considering hydrogen evolution exchange current density on zinc surface also. Now, when we consider this, another important aspect is, since we are considering the material aspect, so of course, this exchange current density would depend on materials. Similarly, it would also depend on the surface conditions. So, these are two important issues we would like to consider. So, one is metal surface and of course, a kind of metal. So, let us put it in two ways. One is metal, which is type, depending on zinc, platinum or palladium or gold, this I0 would change for a particular reaction. Second is metal surface. So, the metal surface condition would also change the I0 for a particular reaction. So, this is surface condition, I would say, surface morphology. So, let us look at these two situations. One case is metal surface, depending on the type of metal. Let us say we consider this reaction, this hydrogen evolution reaction, let us say this we call it HER, hydrogen evolution reaction. Now, depending on this reaction, we can constitute a cell which is called standard hydrogen electrode. Which we, in short, we call it as SHE. And when we talk about standard electrode, standard hydrogen electrode, we need to also see the what is the importance of this standard hydrogen electrode as well as its constitution. So, it looks like this. Schematically, you have a acid solution where can make it as H2SO4, where H plus ion concentration is maintained at 1 mole. Now, this is a glass, simple a glass electrode, where this is a metal wire which is connecting a platinum plate which is dipped in acid medium, and through this route we send hydrogen gas, and that pressure is maintained as 1 atmosphere. And when we do that, that time we get potential would be E0 plus RT 2F ln ox red, which is E0, and if we consider 25 degree Celsius and 1 atmosphere pressure. So, then this quantity would become 0.0591 divided by 2, and that time this quantity, this is be in terms of log instead of ln, and then ox is nothing but H plus ion concentration square and pH2. The reaction is H2. Now, this is maintained at 1 atmosphere. So, it will become, this is 0 minus 0.0591 pH. So, these two, they will get cancelled. So, this is the equation. So, finally, we are getting E equal to minus like this, and I would like to put this 0 value. Now, when this is maintained at 1 mole, 1 molar solution, so then this goes to 0. So, E equal to 0 volt. So, now once we maintain this E0, so if it is connected to, let us say, another cell with a salt bridge, this is the salt bridge, and if we have a zinc rod here, see, if we connect like this, this is zinc sulfate, we would see some voltage here, and this voltage is the difference between the electrode voltage between this one and this two. So, here we have electrode voltage which is E2. Now, if we maintain this situation 1 molar as well as 1 atmosphere hydrogen pressure, then E2 would be always 0, and that is what the E1 is nothing but E1 minus E2, which is the difference between these two electrodes, is equal to E1. So, now this becomes my unknown electrode potential. isn't it? So, that is the use of the standard hydrogen electrode, and why we are calling standard, because we are maintaining 1 atmosphere pressure and 25 degrees Celsius, and the activity or the concentration of hydrogen ion is also maintained at 1. So, now in order to maintain, so we have to make sure that this particular cell stays at 0 volt all the time. That means that standard reduction potential for this reaction in this particular hydrogen electrode is to be maintained at 0 volt. In order to do that, we have to maintain those concentration as well as pressure. Now, if we, and this is taken as platinum. Now, if we take some metal, and why we take platinum? Because the on platinum surface it is around 10 to the power minus 1 to 10 to the power, rather 10 to the minus 2 to minus 3 ampere per centimeter square, which is considered to be very, very high current density. Now, what is, why we should choose, rather we should choose some particular metal where this hydrogen reduction exchange current density should be very, very high. Now, what do you mean by very, very high, and what is the advantage of very, very high? High value of I0 for this particular hydrogen reduction reaction or hydrogen reaction, which is the half cell reaction. Now, when we have this, then if we see the rate part, let us say this is the time and this is the rate. Once the metal is introduced in a solution, so this metal ion would form. So, or other way around, if we have the solution maintained at with the metal ion concentration maintained with some metal ion presence there, so then there could be reduction reaction as well as oxidation reaction. So, reduction reaction is nothing but Mn plus Ne equal to M, or oxidation reaction M minus Ne equal to Mn plus. So, these two reaction would happen. Now, let us say initially the reduction reaction would be very high, because we have already the presence of Mn plus. Depending on its reduction potential, Mn plus would try to reduce and then form M, and as this reaction is starting, this reaction would also start, but they will be sluggish in the beginning, but as the time passes on they will pick up, the rate will pick up. So, and the forward reaction, which is this reaction, the rate would reduce. So, Mn plus Ne M, this rate initially would be very high, because already there are Mn plus ion presence, and then initially this particular reverse reaction, which is M going to Mn plus, would be less, because initially if I assume that the first the Mn plus would ion would get reduced first, and then metal would release electron and then form metal ion. So, this is rate 1 and this is rate 2. So, rate 1 is nothing but IC, because this is the cathodic reaction, and rate 2 is IA in terms of current density, if we would like to express them. So, the IC, the first rate is this one, and then second rate, this is rate 2, this is rate 1. Now, at some time, after some time they will reach equal, and then they maintain if we do not disturb the equilibrium, because they would reach equilibrium. So, this is the condition which is basically the equilibrium rate and or I0. This is IC, this is IA. And now, interestingly, you see this I0 is arriving at this time, this is the time, let us say T0, and this of course happens on a metal surface, that is same metal surface. So, this is for this particular redox reaction. So, similarly, if we can consider this hydrogen reaction, here also this forward reaction and backward reaction, they will reach equilibrium after some time on a particular metal surface, let us say metal 1. Now, this on metal 2, this is I 0 on metal 1, I 0 on metal 2, and when we consider about I 0 metal 2, if I 0 metal 1 is less than I 0 metal 2, it means that equilibrium on metal 2 for this reduction reaction or this particular half cell reaction would arrive at a much faster time. So, means it will arrive here. So, that means this is my new I 0. You see the I 0, this is on metal 1, this is metal 2. So, that means I 0 in case of metal 2 arrives at a much faster time. This is, let us say, T 1. Now, what it indicates? It indicates that the equilibrium achieves or is arrived at much quickly in case of higher exchange current density. So, higher exchange current density indicates early now early equilibrium also indicates this particular early equilibrium also indicates that let us say somehow on this metal 2 surface we disturbs the equilibrium because of some situation, and since it has got a higher I 0 like the situation what we have seen, higher I 0. So, the equilibrium will be re-established much quickly. Now, interestingly, when equilibrium re-establishes quickly, it indicates if E is disturbed, so higher exchange current density, it indicates early equilibrium, and early equilibrium indicates that if the equilibrium is disturbed by some means, it will re-establish quickly. What is the importance of that part? Now, this particular cell is basically a reference cell, which is the hydrogen reduction standard hydrogen electrode, and in case of standard hydrogen electrode, we have to maintain this voltage which should be known beforehand, otherwise we cannot know the potential of the unknown electrode. So, in order to know that, in order to maintain this particular potential all the time, similar potential and known potential, we have to also see that that potential is stable, and in order to make it stable, we have to also see that the equilibrium is reached quickly, because this potential is actually condition of indicating a condition of equilibrium. This also indicates a condition of equilibrium. So, and that means indirectly it also indicates that it has to have a non-corroding reversible condition, and when it is a non-corroding reversible condition, that means it is also related to I 0. So, higher I 0 means the condition of equilibrium is established, and if there is a disturbance, then higher I 0 also indicates that condition of equilibrium will be re-established quickly. So, all the time we can maintain this standard reduction or standard potential or standard reduction potential to be at the known potential. So, it will help us in determining the reduction potential or the electrode potential of some unknown cell. And there could be possibilities that that equilibrium is disturbed by some means during the experimentation, during measurement of this unknown electrode potential measurement. And since platinum has got a very high reduction exchange current density of hydrogen reaction, it will re-establish the equilibrium, and so we will be okay with this reference electrode. Now, if I try to see platinum as well as zinc. Now, in that case, on zinc for this particular reaction, I0 is of the order of 10 to the power minus 11 to 10 to the power minus 13 ampere per centimeter square, and here it is, as we have mentioned, is equal to 10 to the power minus 2 to 10 to the power minus 3. And also, if I try to see the values of I0 on top of, let us say, iron, it is of the order of 10 to the power minus 6 ampere per centimeter square. I0 of hydrogen reaction on nickel is of the order of 10 to the power minus 7 ampere per centimeter square. So, these are the values. That means, on platinum surface, hydrogen reaction would achieve equilibrium quickly compared to zinc surface. It will take much longer time, and when it takes much longer time, that means if we make some standard reduction cell with by using zinc, it will not be a good practice, because it will take long time to establish equilibrium, and then if somehow equilibrium is disturbed, it will also take long time to re-establish that equilibrium. So, that is what the platinum is very much preferred electrode for hydrogen cell, hydrogen standard electrode. Now, instead sometimes we use platinized platinum, and in case of platinized platinum, so I0 for this hydrogen reaction is much higher than I0 on platinum. See, when it is platinized, on platinum, platinum is plated. So, when platinum is plated, it actually forms a very rough surface, and it means that if we have a particular area of platinum, and if it is platinized platinum, so then the actual area increases. If we see this one from cross section, so it would be look like this. So, this is the cross section from the side if you look at. So, actual area increases. So, here actual area increases, which leads to much higher hydrogen reaction, or I0 increases. It suggests that if we use platinized platinum in place of platinum, standard hydrogen electrode would be much better compared to if we use platinum, because in case of platinized platinum, I0 is higher. So, the equilibrium would be much stable equilibrium, or if we disturb this, it will come back to the equilibrium quickly. So, that helps us to maintain the standard potential of that hydrogen electrode, so that we can measure the another potential of an electrode with certainty or surety. So, this is about the effect of different electrodes, different metals, as well as the surface conditions. So, now there are other factors on which this exchange current density depends. It depends on, as we have said, metals, type, morphology of the surface, then we have temperature, environment. Why environment? Because sometimes we have a situation like in one place we have higher salt content, or in other place we have less salt content. Then for example, in seashore area salt content is very high, and if we go to Himalayan belt, the salt content would definitely be less. So, in those two cases, even we use the same temperature and pressure and the same metal and solution, we would have a difference in exchange current density of a particular reaction. And then we have solution concentration. This would definitely change the exchange current density also. So, these are the some of the factors on which density. So, we will talk about exchange current density more in our next lecture. So, let us stop here. Thank you.